Hey everybody, this video lesson is going to talk about the periodic table and some trends that we can see on the periodic table. Trends that you can observe when you look across or down the rows and columns of the periodic table. First, let's talk about a little bit of the structure of the periodic table. A group or a family of elements are in the same vertical column. Oftentimes we call these groups, sometimes they're called families, but a group is a column, and there are 18 of them on the periodic table. Periods are horizontal rows of elements. Periods are less important than groups in the periodic table. Elements are grouped together by similar properties and similar traits, so they're similar vertically more so than they are horizontally. Now, the periodic table is basically divided into metals and nonmetals, and about 80% of the periodic table are metals, and the other 20% are nonmetals, or there's a series of elements in between the metals and nonmetals known as the metalloids, which are not really metals and not really nonmetals. They're called semiconductors. Metals are lustrous, which means they are shiny, malleable, they are bendable, they're good conductors of heat and electricity. Nonmetals, on the other hand, are dull, less shiny, they're brittle, they break, and they are poor conductors of heat and electricity. And then there's those metalloids, which are a barrier between the metals and nonmetals, and those are semiconductors. Examples of those include silicon, arsenic, and boron. The periodic table is organized, as I mentioned on the last slide, by patterns of properties. Elements in the same column of the periodic table have similar bonding characteristics and also similar characteristics of chemical and physical properties. The person who's credited with organizing the periodic table as it is today is a Russian teacher by the name of Dmitry Mendeleev. Now, the periodic table is read from left to right, top to bottom, and those elements increase in order of atomic number. No two elements on the periodic table have the same atomic number. The atomic number identifies the element. If you see a symbol of an element, the atomic number is usually written in the lower left-hand corner, and the mass, which is the mass of the protons plus the neutrons in the nucleus, is written in the upper left-hand corner. And this section right here, where I've labeled a box, is used for identifying the charge of the element. As I mentioned a number of times now, elements in the same group have similar properties, including common charges, so they form ions similarly because they have the same or similar number of valence electrons. The first periodic trend that I'm going to talk about is called the atomic radius. Now, atomic radius is basically the size of an atom, and the atomic radius decreases as you move from left to right on the periodic table. Now, if you look at a periodic table, the atomic number increases as you go from left to right, so you would think that the atomic radius increases as well. But just because the number of protons goes up doesn't necessarily mean that the size of the atom goes up. As you go from left to right, what you're doing is you're adding more protons, but you're also adding more electrons. And when you add more protons and more electrons, you get a stronger pull between those oppositely charged particles. And that results in an increased effective nuclear charge. This increases when you add more electrons and more protons to the nucleus. The more you have, the tighter the pull. And the tighter the pull, you decrease the size of an atom. The effective nuclear charge is the attraction electrons feel towards the nucleus. So let's concentrate on the yellow pictures in each one. As you move from left to right, you can see the size of the yellow circles goes down, 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 because you are increasing the number of protons and increasing the number of electrons and increasing the effective nuclear charge as you move from left to right. So they decrease going down. Now take a look at the trend going down the column. They, in fact, increase. And the reason that they increase is because as you move down a periodic table, as we talked about in the last video lesson, you're increasing an energy level of electrons. So you're increasing having more shells. And more shells, the electrons are further from the nucleus. So shells have, even though you're adding electrons, adding more shells in areas further from the nucleus means that these atoms are getting bigger. As you move from left to right, you're adding more electrons, but they're all within the same shell. And the result is they pull in tighter. But as you add electrons on different shells going down, it results in a bigger atom. Going down a column, the larger elements are at the bottom. Another thing that comes into play is something called electron shielding, where a core electron soaks up the nuclear charge that a valence electron would feel from the nucleus. Here's a picture at the bottom of the screen. You've got the nucleus, and then the first energy level has 2 electrons on it. Now, if I add another electron energy level, it would come just outside the first energy level. We'll call it the second energy level. And let's just say that these electrons, there's 4 of them. Now they're going to feel an effective nuclear charge to the nucleus, just like any electron feels a pull to the positive nucleus. Now let's take, for example, another nucleus of a different atom, and the valence electron is trying to pull in close to the nucleus, just like the valence electrons were on this side. But what's different is now there is a row of electrons in between the valence shell and the nucleus. In fact, there's 2 rows of electrons. On the picture on the left, there was just 1 row of electrons, or 1 shell of electrons between the valence shell and the nucleus. And there was not much shielding. There was some shielding by this first energy level, but not a lot. But as you increase energy levels, you get more shielding, and that basically soaks up the effective nuclear charge, or the attraction to the nucleus. And as a result, the valence shell gets further and further from the nucleus. So shielding, electron shielding, causes an increase in atomic radius as you go down a column. Shielding is not the reason why atoms get bigger or smaller going horizontally across a row on the periodic table. That is attributed to the effective nuclear charge. Electron shielding is only used to explain why atoms get bigger as you go down a column on the periodic table. And it would be incorrect to use shielding as an example or an answer to explain a trend in atomic radius across a period. Now, along with atomic radius, I'd like to talk about ionic radii. Ionic radius is, again, the size of an ion. It's like the size of an atom, but it's the size of an ion. Now, we can't talk about cations and anions the same. You can compare cations to cations and anions to anions, but you can't compare cations and anions together. So let's first talk about cations. Now, in the formation of a cation, a neutral element like sodium, which has 11 protons and 11 electrons, will lose an electron. And when it loses an electron, it has less negatives, but keeps the same amount of positives. As a result, it has less negative charges to keep track of, and it pulls the atom in tighter. And so a cation will lose an electron and become smaller than its parent. We typically call the neutral the parent, and we call the resulting atom or ion the daughter. So the daughter of a cation is smaller than its parent, because you have less electrons total sharing the same number of protons. Think of this analogy. If you're walking 2 dogs, 1 in each hand, you have a pretty good chance of holding on to each dog and keeping them close to you. But let's say you got rid of one of the dogs, like you sent it home and dropped it off, and you just took your single dog for a walk. You have a much better control of 1 dog than you do over 2 dogs. There's 1 less electron to keep track of, so you have better control over it, so you can keep it in a tighter radius. Just like you have 1 less electron, you can keep it closer to the nucleus. Now with anions, it's opposite. Anions are bigger than their neutral. The neutral, or the parent, is small compared to the daughter. In this case, you have more electrons than you need to keep track of, and the nucleus has a harder time holding on to them, and so the radius is larger. Let's take the same dog analogy. You're holding on to 2 dogs, 1 in each hand. You got a leash in each hand. You're walking them down the street, and you got a pretty good hold on them. But let's add a 3rd dog into the mix, and now you have more dogs that you need to keep track of. You will have a harder time of keeping those dogs close to you because there are 3 of them rather than 2, unless, of course, they're very well-behaved dogs. But in summary, gaining electrons results in a larger ionic radius. Now let's revisit this picture once again, and now let's focus on the ionic radii. Now the same trend that you see in atomic radii as they get smaller going to the right is true of ionic radii, but we can only compare the cation radii here. It gets smaller going to the right for the same reasons. You are increasing the effective nuclear charge going to the right. You in fact have more protons pulling on the same number of electrons. Remember, a +1 charge ion lithium has 3 protons and 2 electrons. Beryllium has 4 protons and 2 electrons, and boron has 5 protons and 2 electrons. So you're keeping the number of electrons the same, but you're increasing the number of positive charges. So you can pull those electrons in tighter because you have more protons compared to the number of electrons. The same as with the next row down. Sodium, magnesium, and aluminum get smaller going to the right. Potassium and friends get smaller going to the right. Going to the right is always smaller for cations. And likewise, going down the column, ionic radii increase going down the column. Once again, because you are increasing the principal quantum number of that valence electron, those valence electrons, and there's increased shielding because there's more electrons between the valence shell and the nucleus. Now let's compare ionic radius, or ionic radii, of anions, and likewise they get smaller going to the right, although not as much. 1.70 to 1.67, this drop is not all that significant, but they do get slightly less size going to the right, and they do get slightly bigger going down. And so the trend for anions and the trend for cations is the same for atomic radius as it is for ionic radii. Let's take a look at a couple of questions that deal with effective nuclear charge and the shielding effect. The first one is a pretty straightforward question. Which should be the larger atom, lithium or hydrogen? And as we talked about before, since these two elements are in the same column of the periodic table, as you go down, you should have a larger atomic radius as you go down the periodic table. But now the question is why? The question is why has nothing to do with its position on the periodic table. You need to talk about the structure of lithium compared to hydrogen. Why is lithium larger than hydrogen? And the answer is because its valence electrons are further from the nucleus because they're on a higher energy level. If I sketch out the electrons of lithium and hydrogen, as you can see, lithium has 3 electrons, and its electron that's valence is on the second energy level. And so it's being shielded from the nucleus by the 2 electrons on the first energy level. Now, you compare that to hydrogen, which has 1 proton and 1 electron. It has no electrons shielding this first electron from the nucleus. It's got free reign, it's got a free path right to the nucleus, and so there is no shielding. So the reason why is because lithium experiences shielding to the nucleus, and its valence electron is on a higher energy level, whereas hydrogen experiences less shielding, and in fact you'd say it experiences no shielding at all. Now every year, this next question seems to trip up my students. So once again, I recommend that you sketch out a picture and explain it using the picture. So this one says, which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Now lithium has 2 orbitals. It has a 1s and a 2s, but we're just simply specifically talking about this orbital right here. I'll highlight them both in red. Is it the 1s of the lithium or the 1s of the hydrogen? Once again, let's talk about effective nuclear charge and shielding. Now, since we're both talking about 1s orbitals, they're essentially both shielding the exact same. There is, in fact, no shielding because there are no electrons between the 1s orbital and the nucleus. So you can't say that shielding causes one to be greater or smaller. Now we need to talk about the effective nuclear charge. Which of these would have more pull on the electrons to the nucleus? Would it be the one with 3 protons pulling on 2 electrons, or would it be the one with 1 proton pulling on 1 electron? And if you said the one on the left where 3 protons are pulling on 2 electrons would pull it in tighter, you would be correct because there is a stronger effective nuclear charge. You have more protons pulling on more electrons in the lithium, and as a result, hydrogen, although it has less electrons and less protons, would actually have a larger 1s orbital. So all 1s orbitals are not the same size. They are affected by the nuclear charge. All orbitals are not equal. A 2p of one element is not the same size as a 2p of a different element. You can compare the sizes of the orbitals just like you can compare the sizes of the elements or the sizes of the ions. And why is hydrogen larger? Because it experiences a lower effective nuclear charge. Now remember, on that slide, there's no quantitative value with effective nuclear charge. You just say it's more or less than what you're comparing it to. And because lithium has more protons pulling on more electrons, it has a smaller orbital radius, whereas hydrogen has a larger orbital radius. And this last one is one that we can talk about by using what we learned in number 2, we can talk about number 3. Remember, lower in energy means that it is closer to the nucleus. So in fact, lithium's 1s is closer to the nucleus, so it has a lower orbital energy. If you were asked why, you would say it's closer to the nucleus because it experiences a higher effective nuclear charge compared to hydrogen, which has less protons pulling on less electrons. I don't think we answered question number 2. We said it verbally, but we didn't actually draw the answer. So in summary, hydrogen has a larger 1s orbital because it has a smaller effective nuclear charge, but in number 3, lithium has a lower orbital energy because it's closer to the nucleus because it has a higher effective nuclear charge.